All right, this is stream 2 of some Game Boy development, as I'm remaking an old game that I had previously made for iPhone for Game Boy. Stream 1, unfortunately, is lost forever because I didn't realize that on OBS there's a streaming button and there's a recording button, and I didn't realize that you have to hit both if you want to record the stream locally. And also I hadn't set up Twitch to automatically keep the videos. So stream 1's gone. Because of that, let me go ahead and talk a little bit more about what I'm doing here, since hopefully this one will be recorded. Let me also switch to my desktop. There. So about 10 years ago, I had made a gem pushing puzzle game for iPhone. And recently, I have been porting it to Playdate. And in this series of streams, I want to port the game to Game Boy. It's being rebuilt from scratch in assembly, and I'm trying to optimize it for the platform. And in this video, I want to, well, in the last stream, I had started making some progress displaying the maps on screen. And in this video, I want to finish actually getting maps on screen, because this is what the game looks like right now. There's some data in RAM, but it's not actually loading the tiles yet. I'm about halfway there, and I want to get the other half of the way there this session. A change I've made since the last stream is I've added a little, maybe I can show it this way. On the right side of the screen, you can see this agenda view. And it was recommended to me to add this sort of thing to help add context to what I'm doing at a given moment in the stream. I can also update it throughout the stream by just typing this text file. I'll update over there, so that's pretty neat. And let's talk about how I'm going about getting, let me open this up over here. All right, so let's talk about how I'm going about getting the maps onto the screen. Let's see, I've got this view and I added some diagrams to it. Okay, so here's a screenshot of the Playdate version of the game. And the game data, I'm defining these maps as a simple grid of numbers, where a number 1, let me pull this up. Number 1 indicates a solid wall. A number 0 indicates open ground. And then I've got other numbers to represent things like gems and players. And in maps.asm, I've got a map that's that's defined in data here in ROM. It's 1s for walls, 0 for open ground. But to present the level to the viewer, I want to show these pretty terrain tiles that you can see this wall that sort of curves around. There's corner pieces, there's side pieces, things like that. But I don't want to have to manually lay out those tiles in my ROM data. I just want to be able to say a 1 is solid ground, a 0, or a 1 is a solid terrain, 0 is open ground. And I want the game to figure out what the actual graphical tiles should be. I've got this little blue grid here showing what the graphical tiles are. There's a 2x2 grid of graphical tiles for every single gameplay tile. And I need an algorithm that's going to determine which graphical tiles I'm going to use for a given gameplay tile. And in order to do that, I have a, just want to do a little, yeah. Just wanted to make totally sure that I'm recording this stream this time. In order to figure out what graphical tiles I should be laying down for a given gameplay tile, I'm creating what I'm calling a vertex map. Let me turn off the sprite grid to show this a little bit clearer. The vertex map, I'm defining a piece of data for every corner of graphical tile data. And in the vertex map, I am using, actually, you know what? I think that helps me more to have this grid turned on. To define the vertex map, I'm giving it one color anytime a vertex is bordered by an open tile, and another color if the vertex is fully surrounded by solid terrain. So any open ground gameplay tiles will be fully surrounded by one color of tiles, by these green vertices. I don't actually have any fully opaque tiles here, but if there was a fully opaque tile like over here, it would be fully surrounded by purple vertices. But you can see these this is a solid block here in a gameplay tile. It's 1 in the game data, but the vertices are a mix of these purple vertices that are surrounded by solid wall and these green vertices that are bordered by open squares. Using this vertex map, I'll be able to figure out what the graphical tiles will be. If a graphical tile is fully surrounded on all 4 corners by green tiles, then you know that's open ground. If it's fully surrounded in all 4 corners by purple tiles, then it's a solid wall. And then if it's a mix of green and purple vertices, then it's some sort of edge piece. It's a corner, it's a side, it's something like that. In the last stream, let's see here. I made a basic tile set. I wrote the assembly code to, I put it into my build pipeline to generate ROM data from that tile set. And I wrote the assembly code to load the tile set into tile data. And the tile map still doesn't have anything in it. I also wrote assembly code to generate the vertex map. And I wrote the ROM data for a test map. So effectively, I wrote the gameplay data for the test map. I've got the gameplay tiles in there, and I have the vertex map. So the next stage of development is going to be actually picking the graphical tiles and inserting those into tile maps, into the tile map, and then turning the screen back on. And then I should actually be able to see something other than a black screen. Before I do that, however, I did a bit of that was too passionate of a sip of water. Before I did that, before I get into placing the graphical tiles, I did a review after last stream of the code that I wrote, and there's a few things I want to change about the code that I did last time. First, let's see here. What do I have in the agenda? So last stream review, we just did that. So in fact, I'm actually going to say, okay. So first, I just hard-coded the map tile set length because I couldn't figure out how to get the assembler to automatically generate it at the time. I realized after the reason I had a problem with that was because when I was first trying to declare this symbol, I was trying to declare it as ROM data instead of a compile time constant, and I had issues with the assembler because of that. So since I'm now correctly defining it as a constant, it's actually really easy to get the assembler to generate this length for me. So I'm going to declare a symbol called map tileset end, and then this simply equals map tileset end minus map tileset. And that's actually it. So if I reload this, you still see the tilesets loaded there. In order to show that this is working, I'm going to subtract 32. Each individual tile of tile data is 16 bytes in size. And the final tile is actually right now, it's a completely white tile. So that is actually a loaded tile right there. And so I'm going to subtract 32 in order to subtract 2 tiles from the length of the data. So that should cause that tile to fail to be loaded. So let me build that. Reload the emulator, and look at that. The 2 tiles aren't loaded. So I fix it, put it back. All right. So it is now dynamically generating the fact that it's 256 bytes instead of me hard coding it. There, that was a successful sip of water. The reason that this works, anytime you declare a symbol in the assembler, it's a floating map address. Its specific position in ROM isn't figured out quite yet. But what I'm effectively declaring here is that map tileset refers to some sort of address in ROM. Immediately after declaring that symbol, I am doing inc bin of a tileset.bin. So I'm just saying, just take all of the bytes from that file and just dump it in the ROM. And then I'm declaring a second symbol right after it ends. And so that second symbol refers to the address in ROM right after the end of the tileset data. And so this is an address, and this is a second address. And if you subtract the two addresses, you're going to get the difference between the two addresses, which is the size of the data. So I now have a dynamically generated or a compile time generated length of the tile set instead of a hard coded 256. And this is a good thing to do because now if I add tiles, which I will be doing, this will automatically be updated and I don't have to write any code. And I don't have to update the value in here. I just change the image in Sprite, and then when I build the game, this value will correctly refer to the new length. And then later I use map tileset length as an argument for mem copy. And it'll just work automatically. All right, second change I want to make. That's done. The second change I want to make, is that going to update in the... Oh, yeah. So the second change I want to make is to make constants for the gameplay, graphics, and vertex map sizes. So I just, on the last stream, I hard-coded all these sizes. It's never good practice to be hard-coding sizes. These things are going to be constants, so I mean, like, I could get away with it, but it's just better to make constants out of them, and so that's what I'm going to do. So I'm going to declare. This should probably be done in an include file so that gameplay objects could refer to them, but for now, I'm just going to declare them here. I'll declare them as underscored things to be private declarations right now, but I'll probably move them to an include file later. So the gameplay map width we already knew from last time was 11, and the gameplay map height is 10. And then I'm also going to declare gameplay map length equals gameplay map width times gameplay map height. All right, and then where in the code am I referring to that? Let's see here. Like here, I have that hard-coded map size. I'm now going to change that to refer to gameplay map length. And then I don't think I referred, oh yeah. If map x is, and that is the gameplay map width, and then this refers to the gameplay map height. I'm gonna change these two. All right. This will, by moving these into constants, it's going to be more responsive to if I change my mind on any of these sizes. Then let's move this down here. The vertex map, I'm going to do the vertex map next. I'm actually going to change the size of the vertex map after I'm done with this, and it's going to be easier for me to do so once I've made this a constant, because the vertex map is way too wide. It's silly that I chose 64. I'm not sure why I did that. But for now, let's not change it for now. Let's just make these constants. And I'm not sure I'm actually going to use vertex map length, but let's declare it anyway. vertex map width, vertex map height. All right, now where am I referring to vertex map? I know I'm doing it here. This is another thing I'm going to want to change, but multiply by the width, 64. Yeah. So it's vertex map width, which is 64. I'm going to remove that comment because I no longer need to, because it's now semantic. It's no longer a magic number, so I don't need the comment describing what's going on. Vertex map width. That just gets added to it. X times. Okay, and then here, oh yeah, we do use the vertex map length. I think that's it. That's probably going to remain. No, I'll make a bit of a better expression out of that. All right. So we've now made constants out of the vertex map. And then finally, we're going to do the graphics map constants. (22) and graphics map height equals 20. Graphics map length equals graphics map width times graphics map height. All right. Ooh. I should be using graphics map, vertex map length here. Okay. Any magic numbers here? Any magic numbers here at all? Come on, magic. Okay. So I'm not populating the graphics tile map yet, so I'm not really using those constants yet, except here, the Game Boy map width. Do I actually have a constant for that? I don't think I do. I should. It would be a helpful constant. So the background map on the Game Boy is, I think it's 32 wide, right? 32 times 8 is 256. Yeah. So the background map on the Game Boy is 32 tiles by 32 tiles. And it would be helpful for me to have a constant in here somewhere for that. I might declare that later. All right, for now, I'm going to keep that magic number in here. It's 32 times graphics map height. And that is currently 20, so 20 times 32 is 640, which is the previous value, so that should all be correct now. And I did a thing previously where if I load this, it should load a different tile into the first couple of rows of the background map. Yep, there we go. So that's still correct. All right. All right, so I've now declared constants, so that's just better practice. I think that should do it for the constants. So let's go back to agenda, make constants for gameplay, graphics, and vertex map sizes. Done. Okay, the next item on the agenda is making the vertex map 32 tiles wide. So, another thought that I had. I can actually derive the graphics map size from the gameplay map. Like all vertex map and graphics map are both derived from the gameplay map. The graphics map is easy. It's just the gameplay map times 2. Let me go back to Sprite here. Vertex map. So in gameplay map here, you can see I've got a little 4x4 grid chunked out or cut out. And then if you count the blue tiles here, it's 8 by 8. There's a 2 by 2 grid of graphical tiles for every single gameplay tile. So I can write that as an expression instead of a constant here. So this is gameplay map width times 2, and this is gameplay map height times 2. The vertex map is also derived from the gameplay map, but there's a little extra trick to the vertex map. So the vertex map, the thing about the vertex map is I need to be able to address the elements in the vertex map at random. Which means, and when I address them at random, what I mean is I'm going to have an X and Y coordinate in the vertex map, and I want to look up or change the value at that coordinate. So what I need to do is I need to calculate the address offset in the vertex map of that coordinate. And in a 2D grid, the address offset is the base offset plus the Y coordinate multiplied by the width of the grid plus the X offset. So for the Y offset, there's a multiplication involved. It's the Y coordinate multiplied by the width of the grid. The Game Boy doesn't have multiplication natively, and so you have to do some sort of software multiplication. And the thing about software multiplication is it's a lot faster if you can do a bit shift instead of what you almost have to do otherwise, which is like repeated adding. There's a couple of techniques to do addition, but basically it's a lot faster if you can bit shift instead of any other sort of multiplication. So because of that, it makes sense for the width of the vertex map to be padded horizontally to a power of 2. And then the wasted space off to the side is just ignored. I only use like the top left region of it. So all of that thinking was good, and I made use of it in the last stream. But for some reason, I chose 64 as the width. I'm not sure why I chose 64 as the width. 32 is the next power of 2 up from the actual number of vertices wide, which is 23. So what I'm going to do is I'm going to change the vertex map width from 64 to 32. And the fact that I now have all these things declared as constants means I should be able to just change it in here. Let me check one last thing, just to be totally confident in this. It's in this routine. Multiplied by the vertex map width. Yeah. So I'm doing it right there. So I should be able to just change this constant. It's going to work. Now, the actual useful space of the vertex map, what I need to have in the vertex map is equal to the graphics map size plus 1 in each dimension. Let me show that in Sprite right here. So the graphical tiles right here are the blue squares. There's 8 tiles wide and 8 tiles tall. The vertex map is based on the corners of the graphics tiles, which means there's a left and right corner to each graphical tile. And so what ends up happening is you have a vertex for every single graphics tile plus 1. So there's 8 graphics tiles wide here, but there's 9 vertices. So I want to turn that off right now. So what the vertex map needs to be logically is 23 by 21, but we're going to be padding the width up to the nearest power of 2. The nearest power of 2 above 23 is 32, so we're going to change the vertex map width to 32. That was a lot of explanation for just changing this single little constant here. Now, since that's actually going to change the logic, and since I did all this extraction of these constants into these from magic numbers into these declared constants, I want to actually check my work and make sure that I'm still loading it correctly. Previously, in the last stream, I used the memory viewer, went to the correct address, and then copied it out, pasted it in a file. And, that works, but that's a little bit silly. It's better to use the console, I think. Let me try that. And it should have the sim, so... All right, so what's the command to dump a bit of memory here? Examine /count. All right, so it's going to be examine slash, and then it is, what is it? 32 times 21? 672. I might be able to actually put the expression there, but, and then it should be vertex map. Look at that. Oh, ha 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 ha. Except I think this dumped 16 bytes wide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. All right, I think I'm still going to be copying it out and pasting it in document, formatting it. But at least I was able to ask this specifically for what I wanted. So let's open up a new file here. Paste this. And then how do I want to do this? This is tedious manual. Okay. All right, we've got about enough data to start checking. I'm going to add a few more rows, and then we should be able to actually check my work. Maybe 2 more rows. All right. Let's go ahead and delete this now. All right, so intuitively, off the top of my head, this is looking correct already. But let's grab this and copy it in. So let's see here. This is, we get the first one on the coordinate that should be 1. All right, so let's see here. So this is 0, 0. This is 1, 0, 1, 1. Oops. 1, 2. So 0, 1, 0, 1, 1, 1, 2. I think that's about right. And it still has the same overall shape. Looks right to me. All right, yeah, so I think these changes work. All right, then I'm going to call that done. So make the vertex map 32 wide. All right, improve vertex map Y-Coord calculation. So I did another silly thing. All right, vertex map coordinate calculation is this logic right here. So at this point, I had calculated the Y offset, and what I needed to do was then multiply it by the width of the vertex map to get the actual offset in the memory address. This is the multiplication operation, and I just said that it's faster to do bit shifting than other styles of multiplication. In here, I did another style of multiplication. I did a loop. I just added the vertex map width repeatedly based on the Y offset, which works. It does work. And like the overall load time for a level would still probably be under like 1/10 of a second. Like this does work, but this is a little embarrassingly slow. There's a couple of other things that aren't the fastest that they could be. But I think I actually want to change this. I don't want to have a loop in here if I don't have to. So instead of the loop, how did I want to do this? It's a Okay, what I'm going to be doing is I'm going to be taking this value here and multiplying it by, I had just made this into a constant, but I'm about to write code that is going to hard code the multiplication I'm going to do. Right now, the vertex map width is now 32. So what I'm going to do is, in my head, I'm starting to talk myself out of doing this, but I think I'm going to do it anyway. Is I'm going to multiply by 32, which is, you can achieve a multiplication by 32 by taking this number and bit shifting it left 5 times, I think it is. Let's see here. Well, that would actually be less. 1 times 32 is, in decimal is 32. Yeah, so take a 1, bit shift it left. One bit shift left 5 times. 1, 2, 3, 4, 5. Yeah. So taking a number and bit shifting it left 5 times will multiply it by 32. So that's effectively what I want to do is I want to take this count here and bit shift it left 5 times. Now on the Game Boy, there is a swap instruction, which swaps the high and low nibbles, I think is the term. And that can be used in order to or as part of multiplying something by 16 really quickly. And then you just have a single bit shift after that. So that's even faster than bit shifting left 5 times. So that's what I'm going to do. Let's comment this out. And let's say use it to add to HL. So I'm still going to do that part. Let's do DE equals Y offset times 32. Push DE and pop DE. All right, and then what I'm also going to do is, yeah, HL plus equals, say Y index. Okay, so let's say Y offset, which is DE, equals Y index, which is currently in A times 32, and then HL plus equals Y offset, which is in DE. So we're preserving DE so that we can use it as a scratch space for this. So next, what we're going to do. All right, so what's the strategy for this? All right, so let's start by swapping A. Swap the upper and lower 4 bits of A. So I want to do some masking, but I'm going to need to copy it into another register temporarily in order to not lose the bits I'm masking out. And then I'm going to load it back in and then mask out the other bits. So what I'm going to do is I'm going to load it into D. Yeah, let's do that. Load it into D. And then I am going to mask out the low bits. That should do what I want. And then I'm going to load that into E. And I'm going to load D back into A. And then I'm going to mask out the high bits. And then I'm going to put that result back in D. So this is multiplied by 16. So DE equals A times 16. So I'm going to explain the algorithm a little bit here. There's a column by convention I like to align to when I do this. Oh. Yeah. Okay. It's this one. All right, so swap the high and low bits for the fast x16. storing D to preserve bits will mask out. Mask out the low bits, keeping high. Store. He swapped low bits. Store swapped high bits in E. Put temp with preserved bits back in A. I wonder if alternatively I could do an XOR. I think I could do an XOR, right? Instead of these two instructions. It's like I see 4 viewers on the stream and I'm hoping one of them knows Game Boy Assembly and can be like, yes, that's exactly what you do. Let me reason about this a bit. So what I have in D right now is, let's say 1010. This is completely wrong, but let's say, and then in A, since I masked out the low bits, I currently have this. So if I XOR those together, I get 0010. Yeah, I can just XOR them. Let me think about that again, just to be totally sure that I can do what I think I can do. Yeah, if I just XOR it with D, that should give me, okay, yeah, I'm gonna do that. Okay. Put low bits into A. Kind of want to use the word swap. I think that would throw me off if I reviewed it, if I was reading the code again later. So we're going to put the low bits into A. Or let's say throw out low bits. Oh, no, we're throwing out the high bits. Throw out the high bits and putting back low in A. And then store low bits in D. Okay, so that's the multiplication by 16. Now we just have to bit shift it left. So I think, yeah, I'm definitely adding more instructions with this alternative technique instead of the loop. But it should run faster because it's just going to run through the set of instructions once instead of doing a loop potentially up to like 21 times. All right, so in order to bit shift DE left by 1, let's see here, the shift instructions I have. There's rotate, which I don't want. Shift left. SRL is shift right logic register. Yeah. Okay. I think what I want is shift left arithmetic register R8. Oh, I can do it directly on the register. I don't have to load into A first. That's cool. Can I really do that? That is awesome. Can I really do that? Shifts D left. That's carried to the previous bit 7. So we're going to bit shift left E once, which is then going to put its high bit into the carry flag. And then isn't there a rotate left that like shifts the carry in or something? I want this, but I want carry on the far right. I might only be able to do that with A. Okay, I guess this will be a rotate left. That's a panel of emoji. I think that's going to be a rotate left. Oh. Rotate bits and register R8 through carry. So I'm looking here, and it's saying that it's going to put bit 7 into carry, and it's going to move the carry into bit 0. Is that going to move the old carry into bit 0 or the new carry into bit 0? I think it'll be the old carry, right? RLA is the same thing as RLR8. It's just dedicated for A and takes one fewer cycle. Yeah. This is the one that I don't want. Okay. Yeah. So I do want the instruction I was thinking. All right, so this instruction right here will move bit 7 into carry and then move the new carry or the old bit 7 into bit 0. So this is the one that I don't want. And RL-R8 is the one that I do want. So that should be the old carry. So RLD sets bit 0 to carry and sets carry to old bit 7. Yeah, okay. I feel like people who are a lot more experienced with Game Boy Assembly than me would just throw those two instructions right out instead of like researching and checking everything every time, or researching and checking every single instruction to make totally certain. But this should do exactly what I want. This is a very fast 16-bit bit shift, right? And now I'm just kind of wondering how many cycles is this? Is this faster than doing 4 swaps? Or 4 bit shifts? Should be, but let's see here. So this is 2 cycles. This is 2 cycles. So this right here is 4 cycles. It's really probably not worth doing this much optimization, but all right, so let's check here. Swap A is 2 cycles, so 2 plus, I think load DA is just 1 cycle, yeah, plus 1, and an N8 is 2 cycles, and then another 1 cycle, and then an XOR is 1 cycle, and then another 1 cycle. So this block of code here is 1, 2, 3, 4, 5, 6, 7, 8 cycles. 8 cycles to do what is effectively 4 bit shifts left. So in order to repeat that 4 times would be 16 cycles. So yeah, this is faster than just doing the bit shift 4 times. So yeah, swap is a good instruction, y'all. All right. And I no longer need that note. So how long was that? 8 plus 4, so that's 12 cycles in order to do a multiplication by 32. As compared to this one, which would be potentially significantly more. It's like, I don't know how much that is. How much is add HLDE? Add HLDE, that's only 2 cycles, but the jump relative would be like 3 cycles, so 2, 3, like 4, let's say 5 or 6. Like 6 cycles, I don't know, somewhere in the ballpark of 6 cycles per iteration of the loop that would repeat potentially 21 times, which would be 126 cycles. 126 cycles against 12 cycles. This is a clear winner. Let's just make sure that I programmed it correctly now. And if so, then I can move on. So let's do another dump. Might have ruined it. There might be a bug. I think there's a bug. This is definitely different. All right. Now we got to figure out how I did this wrong. Oh, I didn't add it to HL. Okay. So D HL plus equals. Yeah. That should do it. All right. All right, dump one more time. There, I think that's going to do it. Let's grab this. And grab the first one that did work. Looks the same. Gonna try to cross my eyes and line them up. Yeah, that looks like it's exactly the same to me. Okay. All right. There. Okay. So that's the next item. In fact, I'm going to go ahead and delete the old code now, since I'm confident in this new code. And then there's further optimizations I saw that I could do, but it was that one vertex map was the one that I really wanted to do. Okay, so that's the end of me dealing with things from the last session. How long have I been streaming? About an hour. All right, that's cool. Looks like it's probably going to be another 2-hour stream. All right, now I have a vertex map, and it's time to populate the graphics tiles. So I'm going to start by declaring a routine. Populate graphics tiles. This is going to take no arguments. It's going to return nothing. Fills the tiles of the background map based on the values in the vertex map. Oh, and actually this is a private function. So, yeah. Or populate graphics tiles. I suppose I could extract these into separate routines, but they're so small. Okay. So for populating graphics tiles, let's talk about how I'm going to do this. The graphics tiles, this graphic, by the way, I got from the documentation from the tiled map editor, which supports terrain tile mapping using the same sort of algorithm that I'm going to do here. The tiles here are arranged in a very particular order, so that there's 16 tiles here, and in binary, you need 4 bits to represent the numbers from 0 through 15. And this is arranged in such a way that you can assign one of the 4 bits to each of the 4 corners. And so if the top right corner is open, you could assign that a value of 1 in the first bit or the 0th bit. And then the bottom right corner, you assign to the second or first bit, or bit 1, the second bit, which is bit 1. And then the bottom left, you assign to bit 3. and then the top left you assign to bit 4. And so what I'm going to do is I'm going to have a number which is going to be my tile map index, which is going to start at 0. And then I'm going to visit the 4 corners of the vertex map for that graphical tile. And if that corner of the vertex map is open, I'm going to set the corresponding bit in the tile map index. Once I've set those 4 bits appropriately, then I can just assign that value to the tile map at that location. And that will assign the correct tile. I have, in the Playdate version of the game, let's see here. Oh yeah. So this is the Playdate code that calculates the equivalent of the vertex map. Down here, I have the code that is the equivalent of what I'm about to do. Oh no, I do call that. Oh, it's because I don't store vertex maps, so I do those queries live every time. Okay. So this is the rough equivalent of the logic, where I got a typo here. I've got bottom left written out twice. This right here is the top right. This should say top right. Okay. Where the top right is bit 0, bottom right is bit 1, bottom left is bit 2, and top left is bit 3. Okay. So, first step, figure out the pseudocode algorithm. Then it's to figure out how I'm going to decompose into further functions and how I'm going to do register allocation. So, for each graphical tile, let's say, tile index equals 0. If vertex map, and let's say there's going to be tile X and tile Y, we're going to have those properties. If vertex map at, let's see here, I'm going to do this in a very particular order because there's a way that I want to go about expressing this. It's the top left is bit 3. Yeah, top left is bit 3. So first is the top left, which is just at tile Y, tile X, vertex map equals. I think I have it because I should have, it should be 1s, right? Tell me it's 1s, tell me it's 1s. Yeah, it's 1s. Okay, good. If vertex map at tile X and tile Y equals 1, then tile index or equals 8. Top left is 8. Okay, yeah. Vertex map. All right, and so then the next bit is it's the bottom left, right? Yeah, bottom left. So the bottom left is bit 2. And so bottom left is at Y plus 1, and then shift F4. All right. Let's check here. X, Y plus 1. Y plus 1, X. It's a little bit, listening a little bit backwards, but yeah, that should be bit shift left 4. Okay. And then the top right No. The bottom right. Yeah, okay, so the bottom right is bit 1. Y plus 1, X plus 1. So that should be bitwise or 2. Yeah. Okay. And then the top right is X or 1. So this is top left, bottom left, bottom right. I don't like that. All right, and then this is Y plus 1. This is, what's the last remaining one? It's the top right. Top left, bottom right, top right. Sounds right to me. Okay. And then finally, BG map at tile y, tile x equals tile index. That's the pseudocode. Okay. So why did I do it in this order? You can see here I'm logically what I'm going to be doing is or equals 8, 4, 2, 1. What I'm going to do is start the tile index at 0. And then the idea is for each of these 4 coordinates, if the corresponding value is 1, then I'm just going to set the least significant bit, and then I'm going to bit shift tile index left by 1. And I'm just going to do that 4 times, and that will get me my tile index. At least I think that's going to be fine. Like, otherwise I'll just set the bits directly. It might not actually be an advantage to do that in that clever way, but the order will still be fine. So I'm going to need a counter. I'm going to be needing to be keeping track of tile x and tile y. Tile x and tile y are each going to be less than 256, so I can store them each in a byte. So I'm going to do something similar to what I was doing previously. So I'm going to load the number, or BC equals number of tiles. Graphics map length. Yeah, this will be fine. And then is it going to be D is the X? Yeah, D is going to be... Nice, yeah. Okay, so let's see here. Tile X equals 0 and tile Y 0. All right, so tile X, D equals 0, and tile Y, E equals 0. Okay, let's set up the loop. We're going to already have the X, Y. So, all right, so to do important work here. And then we're going to do the looping structure. So we're going to increment D, which will set flag, but that's... Actually, I don't think I actually need the BC count. I don't think I need the BC count because Am I using a BC count up here? BC equals 0. Because I do this work. I think I can... All right, this isn't going to harm anything with what it's doing right now. This is going to be fine. I don't think, in Generate Vertex Map, I don't think I actually need BC. Let's get rid of that. Because I have... because I'm maintaining the map X and map Y manually. And I'm breaking once I finish map X and map Y. Like, this is where the loop logic is going. So I don't think I actually need BC in Generate Vertex Map. Let's just make sure I didn't just break it. Yeah, it's the same. All right, yeah. So that was silly of me. This actually opens up another opportunity for optimization. Because now that I know that I'm not... So let's rewrite this too for each map Y and map X and gameplay map. Yeah, load HL into the address. Yeah. Yeah, that was simple. Okay, so the thing that I could do now... Oh, I should get rid of this because I'm not actually using it anymore. Because of this, I think this routine is not using BC at all anymore. Well, it was using it for the mem set, but it's not important anymore. Because of that, I don't need to preserve BC anymore. Because that loop counter is just not actually doing anything in this routine. I'm not passing it as an argument. Yeah, I'm not actually using it. I'm using this to control the looping logic. This one I'm actually using though. So yeah, that preservation does actually need to happen. Okay, okay. Okay. So I don't actually need this, but I do need I am going to eventually need graphics map index, but that's going to be... No, I know what I'm going to be doing. Okay. So HL equals BG map 0 index. There's something else I'm going to do first. Okay. Yeah, so there's another layer to this algorithm. Just want to run this again just to be totally certain that, yeah. Yeah, I'm still good. All right. Okay, so there's another layer to this algorithm. So one of the game design constraints of levels in this game is that the outer ring of tiles are all solid. Now, an effect of that is that the just inside from the outermost ring of graphical tiles, you can have zoom in a bit here. You can have tiles that aren't just solid wall tiles, but the very most outer ring of graphical tiles are all just going to be pure solid wall. They're never going to have edge pieces of any sort. Because of that, I can simplify how I'm going to be treating the vertex map. Actually, looking at it right now, that's not going to matter because I have a vertex map for. No, it's good. Okay. I was just like, did I write a bug? No, I did not write a bug. My code is perfect. Okay, so at first I was thinking that what I can just do, and I can do it, but it's a little bit clever. I'm not going to do it right now. Is that because every single tile on the outer ring of graphical tiles is going to be a pure solid wall, I can just use a mem set to pull that off. And then my actual algorithm for determining tiles, I could only run on every tile except for the outermost ring. So just the inner tiles, I could run the actual algorithm on that. That would save a little bit of performance because the expensive work wouldn't be happening on the outer tiles. And also, I was thinking at first that it would help me avoid edge cases with the vertex map, because I'd gotten it into my head that like it would, I wouldn't have corresponding vertices for the outermost edge of tiles, but I actually will. So I don't have to worry about edge cases on that. So I'm just going to go ahead and run the full algorithm on every single graphical tile. So what that means I'm going to do is I'm going to HL equals address of first BG map. Down. So load HL mem BG0. Yeah. I think I'm doing a BG0, right? Yeah. I'm saying BG0. Okay. Tile X D equals 0, tile Y E equals 0. Okay, so so tile X++, we're going to increment D. And then we're going to loop if X is not equal to something. X++. If tile X is not equal to it's going to be graphics map width. So we're going to load D into A. We're going to compare it to the graphics map width. If we haven't hit that value, then we're going to loop. We have, so tile X equals 0. Jump forward and jump to next row. Jump HL to next row. Tile Y++. So can I do that 0 out there? Yeah. So load D0. Okay. Increment tile Y, which is E. All right, then I'm just going to do the Y case right now. If tile Y is not equal to graphics map height, loop, load AE, compare graphics map height, jump relative not 0 dot loop. The algorithm is done if we reach this point. As is right now, that should be enough that like the algorithm will terminate. So I should be able to boot and the Game Boy does not freeze. What is the breakpoint? What is the pause command? Just B. Oh no, that creates a breakpoint. Pause. Okay, so now where am I at? Should be. Okay, so not there, not by. Okay, there. I'm in main loop. Okay, so I should be able. Program is running. All right, whatever. I'm pretty sure it's working. Ooh, actually, I've got another idea. Here's a simple way they can pull this off. Not that one. This one. If I see the change tile, then I know that I broke out of populate graphics tiles and my loop works. Okay, my loop works. All right, so we're successfully iterating through tile X and tile Y. Now, what's going to happen is for HL, before I reach the end of the row, I'm going to be incrementing HL on each after the completion of each row. So, or after the completion of each cell. So by the time that tile X equals graphics map width, HL is going to equal all right, so let's pretend for giggles that the background map was 20 tiles wide and that our gameplay map was 5 tiles wide. HL would be equal to 5, and so I would add 15 to jump it down to the first tile of the next row. So it's going to be equal to 32 minus graphics map width. Okay, I added it. 16. No, okay. So I'm not using BC for anything here, so I know that I can load BC. 32 minus graphics map width, and then we can add HLBC. Okay, and so now HL, well, not right now. I still need to increment HL on every pass, on every step of work, but once tile X equals 0, or once we reach the end of a tile X, we'll move that to 0. We'll jump HL forward to the beginning of the next row of the background map, and we will increment tile Y. Okay, so we now have D holding the current tile X coordinate and E holding the current tile Y coordinate. One order launch. And HL is part of the way to constantly holding the correct destination tile map index. In fact, I've got something really quick that I'm going to do. Load A1, load HLIA. I'm just going to write the value 1 into HL, and then I'm going to increment HL. So that should correctly load up a tile map of the correct size, even though the values are wrong. Yes. All right, so how many Y is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. That looks right to me. And then the graphics map should be 20 tiles high. 1, 2, 3. There's an offset here. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, cool. All right. So HL is definitely incrementing correctly. So there's nothing left now except calculating that tile index. What variable do I want to store the tile index in? My instinct is to load it into B. Okay. Tile index B equals 0. Okay. Let's do this. All right. A equals tile index B. Or let's do value at BG map plus equals tile map B through A. Okay. And that is the fastest way to do that, right? Because that's one cycle, and then load HLI, that's 2 cycles, so that's going to be 3 cycles total. The alternative to that would be load HLB, which is going to be 2 cycles, and then increment HL, which would be another 2 cycles, which will be 4 cycles. So that is 3 cycles there, so that is the right way to do that. So tile index B equals 0. So now it should be back to black. Let's throw in 2 just to be cute there. Cool. All right. All right, next. If the vertex map at tilex. All right, how am I going to do this? All right, so the next task is to get the vertex map at these different coordinates. I think I'm going to write a routine to get the vertex map value for a given tile x and tile y in D and E. The question is, what register do I want to store the output value in? My first instinct is to put it in A, since that's just going to be the easiest for me to directly work with. So I'm going to do that. So I'm going to create a function here. Get vertex map value. The arguments are going to be D equals map X, E equals map Y. And it's going to return A equals value. Returns the value of the vertex map at vertex map X, vertex map Y in A. Okay, so for giggles, right now I'm going to do 1. I'm going to return the value 1. So this should be, so what I'm going to do right now, as this isn't going to have intelligent work done in it right now, it's just always going to return 1. So it's going to say, yes, every vertex map value is open ground. So I'm going to finish implementing populate graphics tiles using that function. And that should make it so that it puts white squares everywhere in the vertex map. So tile index at bit 3 equals vertex map tile y tile x. There's going to be some pushing and popping involved. That'll be fine. So we already have D and D as the correct values. So first there's going to be a call to get map vertex value. Yeah. This will be fine. Now, I need to preserve BC because I use that. I need to preserve DE because I use that. And I need to preserve HL because I use that. That's a lot of pushing and popping. But now A is going to be 1 if it's open and 0 if it's not. So at this point, I can just do a bitwise OR with B and then bit shift left B. Is there a conditional bit set? No, there's not going to be. That's clear, and that's set. It's 2 cycles. I'd be doing a condition check, so I'd be doing a comparative. All right, so I'm trying to explore 2 different ways of implementing this. The other idea is to do a little condition check to see if A is 0. If A is not 0, then I just do this set. The condition check is going to be 3 cycles plus 2, so it's going to be 5. And the compare is going to be 1. It's what, like 6 cycles to do it this way, and to do it with a conditional jump. Yeah. 3, 5, 6. Okay. So doing the conditional technique. Doing the other technique that doesn't involve it would be or B, which would be 1 cycle. And then we will rotate A, which will be 1 cycle. Yeah, it's going to be better without the condition, without the conditional jump. And then there's also SLA, which is 2 cycles. Isn't there like just a shift? Yeah. RLA will be best, and that will work. Rotates A left says bit 0 sets carry to old bit 7, but since B is going to start at 0, it's not going to be shifting anything in. Or B, and then load A into B, which is also 1. So this is going to be the technique that we're going to do. We could also rotate left B, but that's going to be 2 cycles. Okay. So B equals A or B bit shift left once. And then I'm just going to get rid of that rotate for the final step. Really don't like all these pushes and pops, but I could write a loop, but I think I could write a loop to pull this off, but I think I'm not gonna do that. I'm just gonna copy and paste the code a bunch of times. Bit 2 is tile y plus 1. So we need to increment tile y, which is e. Going to add just a little bit of extra comment weight to these. 2 equals tile y. Okay. Bit 1 is going to be tile y plus 1, tile x plus 1. So this is going to be tile x plus plus, which is increment d. And then finally, tile index bit 0. Right? Tile y, tile x plus 1. Okay, yeah. Or B, and we're not bit shifting it left. All right, and then in order to get tile X back to its original position, and decrement D to put so that both tile Y and tile D are back at the values they were at the top of the loop. Although I could just not do that. Yeah. Because I just turn it around a couple spaces later, so. Okay, so I should have a big white area here now. I do. It's a little interesting to see it fill in. That's weird. You wouldn't actually see that on an actual Game Boy though, because the display's off. So that should finish the work here. I want to see something. How big is this? It's not looking too bad. Yeah, it's not very bad at all. 100. It looks like it's happening from about. Yeah, this is not a lot of code at all, I don't think. Oh, there we go. That build. I just want to see how big my code is right now. CF is like, it's under 256 bytes. This is not bad at all. All right. I think it's time for the very last part of this algorithm. We're almost to the finish line. Okay, we're in a routine here. We can safely use any register. We have D and E set. I'm going to refill my cup of water real quick. I'll be right back. Awesome. All right, I'm back. All right, we are almost done here. We are almost done here. So we just need to get the value of the vertex map at that coordinate. So HL equals address of vertex map. Load HL vertex map. HL plus equals Y offset. I'm going to use BC for that. Let's see here. I should actually be able to just copy and paste some code from up here, which means it's a good candidate for extraction, but HL equals the address of vertex map. A equals map Y. I don't need to do that because I have the direct coordinate. Oh, I don't have to do anything there. Yeah, I'm going to be doing this. I'm going to be generate from this. So I'm going to do it based off of BC equals E, because we're going to be doing the Y offset right now. BC equals E, and then BC bit shift left. Load A to E. Can I just destroy that? That should be fine, right? Yeah. It's fine for me to destroy this value because it's going to be preserved outside of it. So swap the high and low bits. Load it into E. Or load it into A. That's got the low bits. And then we're going to store the swapped high bits into C. Throw out the high bits. And then store the low bits into B. Store the low bits and then BC. CB. Okay. So BC equals vertex map Y times 32. Yeah, that is what I want to do. Swap. Put the swap value into A. Mask out the low bits. Put the low bits, or put the high bits into C. XOR against E to get the other set of bits. Put that into B. And then do a 16-bit bit shift left. And that gets me my Y offset. All right. And then adding X is easy. X offset EC equals just D. And then yeah, I'm not going because this is just a one-off routine. I don't I don't need to increment A. It's not I don't need to increment HL. It's not going to get me anything here. The value of the vertex map Y, vertex map X. And then we should return. And then that, I think, is it. I think that's it. I think that's it, guys. Moment of truth. What is that weird pixel? There's a weird pixel. I think that's a problem with the art. Yeah. That should look like that. All right. Reload. Works. Okay. Oh, that was so much assembly programming. And that looks right? Like there's this little shape here. There's what's going on here? Oh yeah. That should still be treated as an open tile. So it should be yep. This little gap here. Then there's a little leg out there, and then there's a solid block just sitting in the middle there. That looks like my data. All right. So the next thing I'm gonna do is just gonna be this real quick thing. I'm just gonna scroll the background map scroll register. What is that? The window scroll registers, the background map scroll registers. I'm gonna scroll some registers to the right and down 8 pixels. Because I have the gameplay map one gameplay tile wider and taller than the actual Game Boy screen. And I'm just going to scroll 8 pixels, so it's just seeing the inner 8 pixels of each of the outermost gameplay tiles. So I'm just going to throw in a little scroll right now. I'm going to go ahead and do that in here. I feel like I should really do it here. So all right, so that's, what is it? Our BG scroll X, A, and BG scroll Y, A. That should offset the scroll registers by 8 pixels, which should, that's exactly what I want. All right. Wow. So much work, but now I can say done here. And I can say done here. Now, I think I just need to make the tiles prettier. So, what I need here is I need a few more colors. Let's just give me 2 more colors in the tile set. Let's make this index mode. Like this very minimal tile set I know is logically correct, but I'm making a Game Boy game. I've got 2 more shades of gray that I can work with. I want to make some more natural looking tiles. So there we go. We're going to be editing tiles or editing colors. So this gray value is going to be, what is it going to be? 85. This gray value is going to be 170. Whoops. Okay. All right, so the shadows in here is going to be lighter colored in the top right corners, darker colored in the bottom left. So I feel like the way it's going to be, I think I'm going to want dark gray as the base background color, and then a black outline. And then dark gray on, okay. Is that what I want? It's gonna be light gray here. It's just, this edge is light gray, this is light gray, this is light gray, light gray, light gray. Yeah, everything on the top and right is light gray. Then all of that is dark gray. I don't know what to do about those right now. This is right. This could be completely backwards. See? That looks right to me. Okay. And aesthetically, I think that looks all right. So now what I'm going to start doing, reduce this to 1 pixel. Just going to start filling in some irregular noise. Let's do that, and then add in some more there. All right. Then yeah, something like that. And then I'm going to add a black outline. In fact, I think to make it look a little bit more organic, even going to add in white corner there. I think I'd need to do more than the white corner. Or actually, this should just be pure black. Let's eat into it a little bit more. That looks horrible. Let's move on for now. Let's just keep iterating. It's the same sort of story here. We're going to have black outline there, white there. Scribble in here a little bit. We have some white pixels here, and the last corner is over here, some white pixels there. Fill in a bit more gray there, gray there. Some dark gray here. Some dark gray here. And drawing some outline here. I want a solid line there. And there. It's more solid there. Starting to come together. Let's do some scribbling there. I think those corners are going to need some adjustments. I don't think that's quite how I'm going to want them to look, but and some more gray there. Add in some black outlines. All right. I mean, that's already looking a lot better. All right, let's fix up these corners here. What is going on with these corners? So the top left one should be bright, but that needs a dark bottom edge, and that needs a dark right edge. I think I could be completely wrong. Let's see. Yeah, I got those backwards. All right. I want to add more of a ragged edge on the straight pieces to make that look a little bit more organic. So let's just go in here. Let's make that 3 wide. Let's make that 2 wide. Maybe an extra 2 wide there. Let's make that 4 wide. Just a 2 wide in the middle. Okay. Reinforce the outline. Okay. Thinking a couple of things. I think I want to push in. I want to be showing more of the side walls. In fact, for perspective, like the bottom edges, these dark gray bottom edges, you should be able to see quite a bit of them, but then the light edge on the top, you should only be able to see a little bit, just because of the perspective shift. So let's see here. Let's pull that in quite a lot, and then let's take that and make it really big. Maybe go all the way up to the edge there. All right, and then I also want the corner pieces here. All right, and then the bottom right edge, same sort of deal. Like this fella should be going way vertical here. Okay. All right, still a lot of adjustments to do. Let's make the side views a little bit wider. The side pieces, the left and right edge, wall edges a little bit wider. fella should come in a little bit. All this just out, and maybe not that much. Let's round out that corner a bit more. Pull that edge out a little bit more. Corner pieces, the inner corner pieces need quite a bit of work, but I think we're starting to get somewhere looking kind of decent. So let's see here, this is 3. And this is... Okay, so I think these corners might actually be fine. It's the bottom corners that need to be made like a lot bigger. I think because this fella's lining up against this fella. So let's make that. Like that. This fella's lining up there. Okay, that's a lot better there. And then the other inner corner that I want to adjust. Actually, I should round it out a bit. Like that. Round it out by a single pixel. It helps. Maybe just one more pixel there. Whoops. Yeah, all right. Now the other one is just the pure dark gray inner corner in the bottom right corner I want to adjust. This fella. It's going against. Let's see, this fella's meeting up right here. So it's 1, 2. Let's see here, I want to do that. All right, and then the bottom edge here is meeting up against this huge piece here, so add. Let's go ahead and pull that down a little bit. It's maybe not actually nearly as big as it should be, but it's an improvement. I think the bottommost edge might be a little bit excessive. Might be a little bit out of bounds and a little bit excessive. Let's pull it in just a little bit. Like that. That's a really symmetrical pattern right now, but let's see how it looks. Yeah, it's too symmetrical, but that's looking a lot better. All right, how do I want to break it up? Like that, maybe? That's not the emulator. Yeah. Yeah. All right. I think that's looking pretty good. So the design alternatives that I can work with here is I could either have a black top surface like this, and like a dark gray bottom and right, or I could have a dark gray top surface and a black bottom and right. I think I'll experiment with that later. I think this is getting to be a pretty good place to wrap up the stream. We're at about 2 hours. So, I want to do one thing first, though, which is that I have brought, let me switch to just the full camera view here. I have brought my Game Boy. So now that we have something that's actually on screen, I want to, I've got an EverDrive here, and I want to put the game on my Game Boy. So, up into this micro SD card. Might need to grab my. In fact, I'm gonna go grab my SD card adapter real quick. I'm not that comfortable with the micro SD card slot on this dongle that I have here, so I'll be right back. All right. Let's see, I've plugged in the adapter. Where's the drive? There's the drive. Now I'm gonna grab the ROM. Gonna copy that over to the micro SD card drive. Right. I'm gonna eject it. Okay. Okay, it's ejected. Let's plug the power back into my notebook. Okay. Gonna put the micro SD card into the flash drive. Okay, select the game. Let's try adjusting the contrast a bit. This is a classic Game Boy. Let's see. I need to be able to see this in real time. Look at that. It is running on an actual Game Boy. That makes me very happy. It's always very nice to actually see it running on real hardware. And there's something about the display, like it's a very bad display, but it's like it's a type of display that you don't use anymore. And so you're not used to seeing your code running on that kind of a display. It's a very strange feeling, but there's just something really awesome about seeing your code running on that type of display. That said, I also brought my Game Boy Advance, which I need to charge. And so here it is on an actual good display. Awesome. All right. Let's switch back to this view. All right, so we finished making the tile set prettier. So that finished my objectives for this stream. So what am I going to do next stream? There's two ideas that I have. One of them is that on the Playdate version of the game, it's a little bit hard to see. Oh, here's a good place to show it. What I actually have is two separate tile sets of the same kinds of tiles. And what I do is I randomly, for each tile, I randomly pick a tile from one of the two tile sets. And that can make things look a little bit more organic because you get less regular repetition. Like here's two ground tiles that are, ooh, I should do that. I should add a little bit of grain onto the ground. that. Nice. All right. And so I can break up some of the repetition by having two different tile sets that represent the same types of tiles, but I can swap between them randomly, and that just makes it look just a little bit more irregular and organic. So I could do that. The other thing to do is to start adding the exit and gems to the tile set and load those tile set types up into the map. So we'll see what I think about doing for next stream. But I think that's going to do it for this stream. Thank you very much for watching, and I'll see you next time.